Okay, I hope my screen is visible to you. Is it? Sagar, my screen is visible to you, right?
Yes, sir.
Oh,
You are visible.
okay. So we have seen what are the elements, what are the nodes, what is meant by boundary conditions. So let us look into the actual procedure of FEM. Okay. So procedure, I can write first step as discretization. And what is meant by discretization? I divide the geometry into small elements, right? So element 1, element 2. So this is whole geometry and I have divided it into small elements. That is discretization. And in this step, type of element and size of element is decided. Okay, so this is discretization. Now that is we were dividing the domain into finite number of elements. Okay, now the second step is deciding shape functions or we can call it as model. Okay, so in this what we do, we'll either go with linear, quadratic, or different type of, like we will decide which shape function we want to use. And here I will introduce you the n matrix n that is called as shape function matrix. Okay, shape function. Here I'm just introducing you to this. In actual, what is it and how it is written, we'll look into it. But here just I am trying to. Now, if I have this f function n, then I can write u is equal to, matrix is equal to n into d. Okay, now this is shape function already wrote. Now this d is displacement or displacement matrix for element. D is displacement matrix for element. Okay, now I have shape function and I have displacement matrix. Now what is u then? With the help of shape functions, what I want to do is, generally, now I have displacement at different nodes. Let us say this node, this node, okay? And inside this element, I want to find the displacement, okay? So our save function help us to find the unknowns inside the elements, right? So this should be displacement matrix within element, right?
Right.
Displacement matrix within element. So done. Okay. So two steps are done. Now the next step. In the next step, we have calculated the in the second step we have calculated displacement. Okay. Now
Okay.
with the help of this displacement, I can calculate my strain, right? If you remember,
Okay.
delta L upon L, change in L or the change in dimension upon dimension is strain, right?
Mhm.
Now this third step, we can call it as okay, let me erase this. It was just for the understanding. Okay. Strain displacement relationship. Strain displacement and stress strain relationship. Okay. Now I can write strain is equal to B into D. This is my displacement into B is my strain displacement matrix. Strain displacement matrix. Okay. B is my strain displacement matrix. And these already told you like displacement matrix for an element. This is my strain matrix, right?
Okay.
Strain matrix. Now, for the simplicity, I can tell you like, let us say this is equal to epsilon, that is strain, that is equal to, let us say, displacement is x upon original length is L. Okay. Now I can write this as like 1 upon L into x. Okay. Now this becomes like displacement matrix, and this becomes like this B matrix.
Strain.
B matrix. Okay. This is just for the simple bar, and this we can write in the matrix bar. Okay. So just for the understanding purpose, I have written this way. Okay. So this is strain matrix, this is strain displacement matrix, and this is your displacement matrix for element. Now, in a similar way, if you remember, our Young's modulus is given as sigma upon epsilon, right? Stress upon strain, if you remember, right? So now I can write this sigma is equal to E into epsilon, right? Now, here, if I want to write stress strain relationship, I can write this way. Sigma is equal to D into epsilon. Okay, this. So D is like this matrix, and this is strain matrix. Now, if I put the value of epsilon from this, I will get D into B into this small d, right? I have just put the value of epsilon here. Now I got sigma. Okay,
Okay.
this d is stress strain matrix, right? So just like for the to remember, here I am giving relationship between strain and displacement, right? So strain displacement matrix, and here I am giving a relationship between stress and strain. So strain matrix.
Matrix.
Okay. Now this is third step done. Now I have
Sir, 1 minute.
yes.
I write down in my notebook.
Okay, I am going to share this video as well and this notes as well with you. Okay, so no worries.
Okay.
You don't need to
Okay.
write. You can after like once I forward it to you, you can take notes from this. Okay, so just
Okay, sir.
try
Thanks.
to concentrate here and try to understand. Okay, now
Okay.
the first step is writing our element equation. Okay. Now I have stress for element, strain for element, and for how I can write element equation. If you remember, for a spring, okay, I have this equation, right? F is equal to K into X, right? F is equal to K into
Right.
X, where K is my spring constant, and this is X is displacement, right? Okay. In a similar way, I can write for element F is equal to K into D. Okay, K is my stiffness matrix. Matrix for element. Okay, so this I am writing for element. So this will be also for element, right? This is my displacement matrix for element, and now this is my load vector or the force vector. Load or force vector, I can, why I'm calling it as a vector, because this is like this matrix 1 2 3 kind of this is like n by 1, right? So that yeah, so I can call it as a matrix as well, but as it has only one column, I can call it as a vector as well. So load or force vector. Now this is for element. Now I will have different elements like this, right? Connected together, right? So how can I write the same equation for all these elements together? Now the fifth step is to write global. This was for the element, and this is called as global equation. Okay, so for now here it was okay for element. If I write the same equation, but here I am assembling this stiffness matrix together, force vectors together, and this displacement vectors together, so that I have this is capital. Okay, this we call it as the same equation. It is same equation, just this is like assembling together. And what is meant by assembly? With example, it will be more clear to you. Okay, now this is global force vector. Okay, this is global stiffness matrix. Stiffness matrix, and this is global displacement matrix or vector. Okay, now I have the global global equation. Now the next step is to write. I have the equation. Okay, now this K is actually a singular matrix. And what is meant by singular matrix? Its determinant is 0. Okay, now with the help of boundary conditions, here I will be writing boundary condition to remove this singularity. And what is meant by boundary conditions? Let us say at this node I will be knowing, here I will be having some force value, right, is equal to, I will be having some here at this node I will be having some displacement constant, like here it is fixed. Okay, if it is fixed, then the displacement here will be 0. So all these conditions I can put here, like if I have a displacement condition, displacement value in, I will put instead of this displacement, and if I have the force value, I will put in this matrix, right? So all these boundary condition I will be putting in the next step. So my next step will be apply boundary conditions. Okay, here let us say if f1 is equal to maybe some 10 Newton kind of, and let us say u1 is equal to 0, u5 is equal to 0, this kind of boundary conditions may be there, and I will put that in these equations. Okay, and in the next step, now I will have these boundary conditions in the equation. Here I will solve solution step. And how can I do that? Let us say, if you remember, 3x plus 5y is equal to 8, and x minus 2y is equal to 6. This kind of equations I have. Let us say I can write these equations in a matrix form like this. Okay, now this 8 and 6 I can write here, or I can write Okay, so 3 I can write here, 5 I can write here, 1 I can write here, and so this is coefficient matrix. This is my variables, okay, x and y is equal to 8 and 6. I can write this way, if you remember. So now if I multiply this with this, so I will get this equations. 3 into x, 3x plus 5y is equal to 8. And 1 into x minus 2y is equal to 6. So this is same thing. Okay. Now with boundary conditions, what I will have, let us say I will have some y is equal to given. Let us say 1. This is my boundary condition. And here I have put the values. So this way it will be given to me. Okay. So now with this, I can find x and y values, right? I can find x and y. So we will be doing the same. We will be solving these linear equations. Okay. And we will be trying to find, we will find primary unknowns by solving linear matrix algebra. And there will be different techniques to solve it. Okay, there will be different techniques to solve it. Once I have these displacements, okay, at different nodes, then I can calculate, I can put these values to calculate my, in the 8th step I can calculate this epsilon. Once I have this displacement, then I can calculate my stress, right? Then I can calculate my reactions. Okay, so
Okay.
these are the 8 steps. Okay, these are the 8 steps. These are the 8 steps. So first step is like discretize, that is divide the geometry into number of elements. Here we will decide the type of element and the size of element. Then next will be deciding the shape functions, and next will be writing the stress strain and strain displacement relationships. Fourth step will be writing element equation. Fifth will be writing global equation, and sixth step will be writing the applying boundary conditions, and 7 will be solving it. Okay, and eighth step will be finding the secondary unknowns. Okay, so this is all, and now we will go to deriving this stiffness matrix. Now here we have stiffness matrix, right? Okay, here we have the stiffness matrix K, and we will be needing this stiffness matrix. Okay, for different problems the stiffness matrix will be different. Okay, now let us say simple we have this rod fixed at one end and subjected to load P, have length A and the cross section area A, and Young's modulus as E. Okay. Now, as I apply this force P, it will display or it will elongate by some X, right? Now, if you remember, I can calculate this elongation as, okay, I have sigma is equal to P upon A, right?
Yes, sir.
Force upon area. So this I have. Now I have sigma is equal, okay, before that I have epsilon is equal to change in length upon L, right? And
Right.
I have Young's modulus is equal to sigma upon epsilon, right? Now putting these values P upon A, and epsilon is x upon A. So it will be like P into L upon A into X is equal to, now I am taking X here. So it will be X is equal to PL upon A, right? So this way I can find the displacement. Now I want to arrange this equation to look like F is equal to K into X. Okay. Now what I will do, I will keep on P here only. Okay. I will keep P on this side. So P is equal to, what it will be like, A into E upon L into X, right? So comparing
Right.
these two equations, I can write K is equal to A into E upon EL, right? What I have done, simply I have written this, I have found the displacement and I have rearranged this to look like a spring equation, okay? So
Nice.
P is equal to A upon L, and now I can say that for this simple bar element, which is axially loaded, I can say that stiffness is A upon L. Okay. Now, okay. This is simple case. Now, I want to derive this stiffness matrix and derivation of stiffness matrix. And I'm sure that we will not be able to cover that in this lecture, but I will try to explain that what are the methods, different methods to find it. So derivation of stiffness matrix. Okay. Now, in this, we have three different methods or three different approaches which we can use. So first is direct approach. Direct approach. Second is variational formulation approach, and the third is residual residual method or approach. we will see one by one these different approaches to find out the stiffness matrix. Okay. Now, let me stop this.